Hello everyone, my name is Diksha and I am from the Bodhi Academy. Today I am going to continue with the HALOALKANES HALOARENES chapter, which is a part 3. So let us start with the first reaction. Reaction with metals. When alkyl halide treated with metal, what compounds we got? So first of all we will cover the Grignard reagent when we get the Grignard reagent as a product. So compounds which contain carbon metal bonds, they are called as organometallic compounds. Okay, meaning we have metal and carbon bond. So this was discovered by one of the scientists, that is Victor Grignard, in 1900, which is called as alkyl magnesium halide RMgX, which is referred to as Grignard reagent. And these are obtained by the reaction of haloalkanes with magnesium in dry ether. So to get Grignard reagent, what are the conditions? We take alkyl halide. To that we react the magnesium and dry ether. So when we have magnesium and dry ether with this alkyl halide, we get Grignard reagent, which is further used in many reactions. So here we get partial negative charge on alkyl group, that is R group, because we treat it with a metal, and metal is electropositive, so that's why R group will get partial negative charge. When Grignard reagent is treated with water, okay, when RMgX or Grignard reagent is treated with water, we get RH. RH is the hydrocarbon. Okay, that means MgX leaves and one of the H comes and attached here, and we get the side product as MgOHX. For example, here if I take CH3 MgBr, to that if I add water, I will get CH3H, that means CH4, which is a methane, and MgOHBr. Then next very important reaction is Wood's reaction, which is carried out when alkyl halide treated with sodium in dry ether. So this condition is required to carry the Wood's reaction, sodium and dry ether. Sodium and dry ether when treated with alkyl halide, okay, two molecules, we get both the alkyl groups attached to each other and along with that the side product. So if I have here 2CH3Br plus 2Na in presence of dry ether, it will give CH3 plus 2NaBr. These are the products. Then next important reactions are nucleophilic substitution reactions, in which we will first study the resonance effect. This is just for understanding resonance effect. So we know that in benzene ring, resonance effect we can see, and whenever there is an electronegative group attached, there is a conjugation which takes place with benzene and that group. So here pi electrons of the ring and following resonance structure are possible. So we can see that chlorine is having 3 lone pairs. So one of the lone pair attacks on the bond, carbon and chlorine bond, and then the next bond shifts over the next carbon. So we get this intermediate with positive charge on the chlorine. Then there is a density on this carbon, so that electron shifts over the next bond and next bond shifts over the next carbon. So this is how the resonance takes place. Now carbon and chlorine bond acquires a partial double bond character due to the resonance and bond cleavage, meaning we cannot break the bond easily in benzene ring. Okay, so they are less reactive towards nucleophilic substitution reaction. Then there are difference in hybridization of carbon atom in carbon halogen bond. So we can see whenever there is directly halogen atom attached to the benzene ring, this is sp2 hybridized carbon, and halogen in this normal aliphatic compound, that is sp3 hybridized carbon. Then instability of phenyl cation. Phenyl cation formed as a result of self-hydrogenation will not be stabilized by resonance, and therefore SN1 will not be ruled out. And possible repulsion, it is less likely for the electron-rich nucleophile to approach the electron-rich aryls. So let us start with the reactions now. Replacement by hydroxyl group. So when we have this compound, this is called as a chlorobenzene. Chlorobenzene, when treated with sodium hydroxide at 623 Kelvin and 300 atmospheric pressure in presence of an acid, we get phenol. Okay, so this is the famous reaction which is called as a Dawes process to prepare phenol from chlorobenzene, and which is one of the very important reaction, chlorobenzene to phenol. Just need to remember the conditions for that. Now since there is a conjugation, there is a very high electron density on this compound. Okay, but if you attach electron withdrawing group to that, then that electron density is decreased. So when we attach NO2 group here, okay, and along with this Cl and add NaOH on 443 Kelvin temperature, we see that NO2 group, OH group get attached along with NO2 group. Now why this happens? Because we attach NO2 group, so there is a less temperature required and also less pressure. So the conditions are reduced now if you attach the electron withdrawing group. Further, if you attach two withdrawing groups, conditions are decreased again. Okay. Then if I attach three electron withdrawing groups, then less conditions are required. So I get warm H2O I can take to carry out the reaction, and all the three NO2 groups with OH I get as the product. Now this is the mechanism which is shown why only they get attached at ortho and para position and not on meta position. So in short, I will explain you all why this happens. So when you do the resonance of these structures, okay, para, ortho and meta, in para and ortho you will observe that the negative charge comes on the para and ortho positions only. So that's why we can carry out the we can get the electrophile attached to the para and ortho position. In meta isomer also we get at ortho and para position the negative charge. So that's why we cannot carry out this meta. We do not get the products as meta. Okay, only get the para and ortho product, as there is a more electron density on ortho and para. So there comes the electrophilic substitution reaction, which are very important based on the mechanism which we have seen. So first of all, halogenation. In halogenation we add halogens. So if I want to attach chlorine, then chlorine will be added along with anhydrous ferric chloride. We get that chlorine attached to ortho and para position. So ortho and para position we get, in that para will be major. Okay, as we have discussed earlier, para is having a symmetry, and that's why it fits perfectly in the crystal lattice. So that's why it is a major product. Then nitration. In nitration we take the respective compound, that is here chlorobenzene, add to it concentrated nitric and sulfuric acid. We get nitro group attached to ortho and para position, and here also para is major. Then sulfonation, we add just sulfuric acid and heat it. We get sulfonic group attached to the ortho and para position, and in this also para is the major group. And next two very important reactions that we have here are Friedel-Crafts alkylation and Friedel-Crafts acylation. What happens in Friedel-Crafts reaction is chlorobenzene is treated with methyl chloride. This methyl group gets attached to ortho and para position of the benzene. So we get a mixture of ortho and para chloromethyl benzene. So here this is 1 chloro 2 methyl benzene and 1 chloro 4 methyl benzene. So this is a para product which is the major product. You have to remember the condition for Friedel-Crafts which are same in all the chapters. If you want to carry out alkylation, then you have to take methyl chloride or alkyl chloride with anhydrous aluminium chloride. If you want to carry out acylation, okay, then alkyl group gets attached here. Then acylation, you have to add this acyl chloride or anhydride, from which this acyl group will get attached to ortho and para position. This condition will be same. So this we get here 2 chloroacetophenone and this is 4 chloroacetophenone. Why it is called as phenol? Because it is a ketone. Okay, so this is acetophenone. Next is reaction with metals. When halobenzene is treated with metal along with alkyl halide and dry ether, this is called as Wurtz-Fittig reaction. Okay, so what we get here, in place of halogen, okay, halogen is replaced by R, that is alkyl halide. Halogen is replaced by alkyl halide, that is we get aryl benzene. Okay, and this is called as Wurtz reaction. We have already seen Wurtz reaction in previous section of this chapter. Now this is Wurtz-Fittig. Okay, because here there is a involvement of aromatic ring. So aryl halide, when treated with sodium, alkyl halide and dry ether, we get alkyl benzene. Example, if you want to see here, I will take benzene with chlorine attached to it plus sodium plus CH3Cl in presence of dry ether. I will get benzene with CH3 and sodium chloride NaCl. Okay, then Fittig reaction, aryl halides also give analogous compound. Now Fittig reaction is just you have to add sodium and dry ether, no need to add alkyl halide. So we take two such molecules of halobenzene, and then to add to that we add sodium and dry ether, we get diphenyl as the product along with sodium halide. So diphenyl we get as a product, which is called as a Fittig reaction. Then polyhalogen compounds. Polyhalogen means when you have more than one halogen atom. So first of all we have dichloromethane, that is methylene chloride. Dichloromethane, only the uses you need to know here. It is used as a solvent or a paint remover and propellant in aerosols. Then it harms the human central nervous system, so exposure to this compound is not good. And direct contact with the eyes can burn the cornea. Okay, so these points you have to remember here. Then trichloromethane, that is chloroform. Okay, chloroform is called as trichloromethane. So here it is used in production of freon refrigerant, that is R22, and it was also used as a general anesthetic earlier, but because of its toxicity it is replaced by other anesthetic. Then breathing about 900 parts of chloroform per million parts of air for a short time can cause dizziness, fatigue, headache, and chronic chloroform exposure also cause damage to the liver, kidney. That's why it is not good, okay, exposure to this gas. Then we have triiodomethane, that is iodoform, then tetrachloromethane, carbon tetrachloride, which these are the mostly used solvents in the laboratory and compounds which are used in many reactions. Freons, which are used in Schwarz reaction. Then para diphenyl trichloroethane, which is commonly known as DDT, which was commonly used or which was used in the World War II, and nowadays we used for the insects, to kill the insects. Okay, so this is a DDT structure. The name is para diphenyl trichloroethane, that is DDT. And with this we finish the chapter haloalkanes and haloarenes. So yeah, I will come up with the next chapter in the next video. Thank you.